Everyone, welcome to this first session of the afternoon on the topics of verification and cost analysis. Our first speaker is going to be Li-yao on story of your lazy functions life. Li-yao, please take it away.
Thank you. So my talk will be about amortized time complexity of lazy persistent data structures. And to start, I would like to present some background, and in particular, the main idea is that here, laziness matters especially in this context. So to start, when verifying data the reasoning about the cost of data structures, the most naive way to do is to do real-time analysis, which is just to look at an individual operation and bound its execution time. Slightly more sophisticated kind of analysis is amortized analysis, where instead we bound the time of multiple operations. And a typical standard example of this kind of structure is a queue using two lists. So to illustrate this kind of reasoning, here the exact data structure doesn't matter, but here we imagine that we have a data structure where we may perform some n operations, and each spend some unit time. Whoops. Well, can you still hear me? And then we have one expensive operation which costs n units. And so here, real-time analysis does not give us a good bound on the operations because they don't cost a uniform have a uniform cost. But instead, we can see that here we have n+1 operations costing in total 2n. So on average, the cost of each operation is still constant. And so to actually prove this, and by reasoning about individual operation one at a time, we try to redistribute the time across the operations using a quantity that we call potential. So here, for the operations that are cheap, we pretend as if they are also create some time quantity that they store in this potential, and then for the expensive operation, we can spend potential in order to offset the cost of this expensive operation, so that when we measure this amortized time, which is the real time plus the difference of potential for each operation, we find that the amortized time of each operation is constant. And what justifies this reasoning is that when you add up the amortized time over all of the operations, you end up with the total real time plus the potential. And so if you know that the potential is positive, then you have a bound on the real time. So indeed, this data structure behaves as if each operation had constant time. Now since we are at ICFP, we especially like writing purely functional data structures which have the property that they are persistent, which means that you can reuse the past every intermediate version of the data structure. And here there is actually a problem when you try to do amortized reasoning for persistent data structure, which is that, well, expensive operations can be repeated. So if we look at the previous scenario where we had managed to prove some constant time amortized bound, now in the persistent setting, we can actually just perform this last expensive operation multiple times. And the resulting time is that for a linear number of operations, you have to spend quadratic time. So on average, the operations cost linear time. So the previous linear constant time bound no longer holds. And that's where laziness comes to the rescue. So using laziness, we are able to write data structures that persistent data structures for which we can prove useful amortized bounds. So here we imagine a data structure where on the first operation, is cheap, but it creates a thunk, so it suspends some work to be done by a later operation. Then some more cheap operations are done to buffer the later expensive operation, which is expensive because it forces the thunk that was created in the first operation. That means that if you repeat this operation, the work done by the thunk is not replicated, so you still manage to get, on average, a constant time per operation. But to reason about this kind of data structure, it's a bit more complicated than the physicist method that I presented previously. You still want to, you still have the idea of distributing time using some logical quantity, which we will call credit now instead of potential. And so, as before, we imagine that the cheap operations generate some credits which we can spend to offset the time of the expensive operation, so that when we look at the amortized time again, all operations cost constant amortized time. The subtlety is that now the credits cannot be freely used like the potential. Here, there is a condition that the credits here can only be used to offset the thunks that have been created before it. So here, if we had some operation that created thunks in the middle here, we couldn't use operations from before here to offset the cost of that thunk, even though all of them, the work that happens to force the thunk happens much later. And because of this subtlety about the manipulation of credits requires some non-trivial machinery in order to work. And so that's kind of the difficulty that we found when we tried to do this kind of analysis. So the banker's method originally by Okasaki is an informal method. And these credits follow some strange rules. And so to be sure that we are doing it correctly, we would like to mechanize our proofs about data structures. And in order to be able to do such formal proofs, we need a formal model of laziness. Now, if we try to do it, now formalizing laziness has been done. There are, in particular, if you think about what is a thunk is really a shared mutable reference that you first store a suspended computation at its creation, and then when you force it, you store the result so that it can be reused. And so a natural way to reason about mutable references is separation logic, and so previous work has indeed applied this idea to reason about laziness using separation logic. And naturally, credits are used as linear resources, which so separation logic is a really natural way of doing this. However, we did not want to do separation logic because we felt that it requires a lot of setup in order to do this. And we found another model of laziness that we call demand semantics, which was published before actually, but there wasn't a lot of work done using it. And in particular, this model is denotational, so we don't have any state to reason about. So we don't have to develop some specialized program logic and and instead we just write the demand semantics will just give us pure functions that we can prove theorems about. And in particular, now we will no longer use the credits of the banker's method. We will use potential so resulting in a variant of the physicist method. So to illustrate the contrast between our technique and techniques based on separation logic, I would like to present another problem in another domain in physics. So here we have we are interested in the trajectory of light as it crosses the boundary between air and water. So, and so as you probably know, the light doesn't go in a straight line from the sun to the fish. When it crosses water, it changes the angle. And so one way to compute this trajectory is to use the fact that light behaves as a wave, but it's quite tedious calculation. And instead, there is a very simple principle that light follows, which is this principle of least time, which is that the light behaves as if it took the, light takes the path that takes the least time. And it's a bit of a strange principle. It was controversial when Fermat proposed it at the time because, as Ted Chiang puts it in his in Story of Your Life, which our paper's title is based on, the ray of light has to know where it will ultimately end up before it can choose the direction to begin moving in, which is weird because light isn't supposed to know anything about where it's going. But the point is that light behaves like this, and we can use it to compute where it's going. And so we have this parallel where essentially the wave equations are an analytical approach based on what is light and how it behaves, and we can indeed infer it, and separation is the same thing. What are thunks? They are mutable references, but the principle of least time instead is a more synthetic approach that focuses on what it looks like, what the behavior of light looks like from a more global point of view, and the demand semantics in a way is similar. So, and so to give you an idea of this semantics, the point is that if you have a lazy function from A to B, the cost of evaluating it depends on, well, how the result is going to be used so that you know whether the thunks are going to be evaluated or not. And so this provides us actually with a translation, syntactic translation, into a function that takes a demand B as an argument and outputs the cost of evaluating the function up to that demand plus the input demand. So what is a demand? A demand is a partial value, which we essentially represent by replacing some of the bits of the inputs or value with bottoms. That represents, where bottom represents the fact that this part of the input will not be needed. So this demand semantics kind of resemble lenses in bidirectional programming. So if you look at this flow, the function itself computes, sends from inputs to outputs, but the demand function f# here takes the output demand into an input demand. And indeed, there are some, when we try to look at the laws that this function should respect, we find some analogs of the law of lenses. So in particular here, the demand function maps approximations of the results. So that means if these are related by some approximation relation, then this final result will be related by this approximation relation. An analog of the put-get law is a bit more technical to make precise, but the idea is that the result here, when we apply this f# function, in a way, when we look at the execution of f in the other direction, what f# gives us is the minimum time in order to, in a way, meet the demand B prime here. So, and so formally, this theorem is really a correctness theorem, a correspondence between our demand semantics and some other cost-aware semantics. And you can look at the paper for details. So to recap, laziness is crucial to amortization and persistence, enabling the banker's method. And we have formalized this demand semantics in order to reason about lazy programs. And so we put these two ideas together in order to reason about the cost of the amortized time complexity of lazy persistent data structures. And in particular, the result of this is the reverse physicist method. Whereas in the classical physicist method, the potential difference is added to the potential of the output so that this potential can be spent by future expensive operations. In the reverse physicist method, the potential flows backwards from the output demand into the input demand, and so the potential is added in order to offset things created in the past instead. And in particular, here, what this allows this potential to do is to, when we have multiple operations on the same input, which is the essence of persistence, the potential will be added so that they can be spent for things used in one branch but not the other. Or otherwise, if the different branches use the same thing, then we just have some extra potential which we can leave unused. To conclude, so we have formalized this demand semantics, and we have proved it equivalent with another cost semantics called the clairvoyant semantics, which has been studied in prior work and related to the natural semantics of laziness. We have shown how to use the reverse physicist method to reason about amortized time for persistent data structures. We have some case studies for the banker's queue and the implicit queue from Okasaki's book. And beyond persistent data structures, we can use this model also to reason about other algorithms involving laziness, such as sorting, and in particular the fact that certain sorting algorithms can be used incrementally to, for example, if you only demand the first element, then you essentially get the maximum or the minimum function, which work in linear time. As a future work, so far I showed that the demand semantics gives us, in a way, correspond to a syntactic transformation of lazy programs into these functions that map output demands to cost. But in our work, we have, in our implementation, we have done this translation by hand, and we would like to automate it to scale up to bigger examples. And there are some limitations that we would like to overcome in the future, such as the support for higher order functions. And our method works for amortized analysis, and we would be also interested in doing some real-time analysis. Thank you.
All right. Since we're out of time for this paper, I suggest that we take one very quick question while the next speaker sets up. So, one quick question, yeah?
Okay, Wouter Svierstra, University of Utrecht. So on the last slide, you showed that you related this demand semantics to the clairvoyant semantics, and this was already shown to be equal to the natural semantics. Great. So what's the property of the demand semantics that you kind of made that you wanted to take that as your starting point rather than taking the clairvoyant semantics for the reasoning?
So actually, prior work, we did some prior work on the clairvoyant semantics before, and when we tried to apply those semantics to reason about persistent data structures, in a way, essentially the work of refining this reasoning ended up resulted in this work where we found that really what we were reasoning about was this demand function rather than the clairvoyant semantics.
Okay, thanks.
All right, you're good on this side. All right.
Okay, thank you. So my name is Jansson. I will talk about level P complexity Boolean functions.